Hi, my name is Akshay Kumar, and today we'll be presenting our final project from Group 5.
I'm Giovanni Guarnero.
I'm Uladzimir Kasacheuski.
And I'll be going over a little bit of our construction of our project in general. So as you can see here, we have our basic requirement of our 4 ultrasonic sensors here, where we made some makeshift cardboard slides where basically it holds our ultrasonic sensors in place and slides on the bottom. And as you can see, nothing moves, everything's in a sturdy place. And what we have here is a shoelace of all places, shoelace of all things, which we use to offset our sensors by 30 degrees apiece, as well as what we use in order to measure our maximum measuring angle. Another thing to note is our external power supply here, which uses a 9-volt battery, which in order to avoid causing any problems for our ESP32 board, we used a voltage regulator here to step it down from 9 volts to 5 volts, which, as you can see, it's powering our ESP32 board with no connections whatsoever to the computer or no serial input whatsoever. And I believe that covers everything. So Vlad here is going to go over the code now.
Okay, so between this project and the previous project, there were 3 main changes, one of which was that we no longer use synchronous weighting to measure the distance. We use a trigger-based functionality instead. A trigger is fired based off of the echo pin. We use a semaphore to wait after triggering the sensor until the echo returns. We use an additional semaphore to make sure that we do not trigger the sensor again if the previous trigger had not had the echo respond yet. The Q functionality of FreeRTOS is used as our shared buffer, but that was similar to the last project. And then the console is implemented mainly using a free library called Line Noise, and this allows the user to update settings parameters that are then used for the rest of the functionality, such as the Wi-Fi information, the sensing period, the buffer size, and it also allows the user to start the functionality, which will start the consumer task, the producer task, the time updating task, and send all that information to a UDP server. I'll let Akshay take it away, showing how it actually works.
Alright, so we're going to go ahead and now look at our serial line and our UDP server line. So if we go ahead and start up PuTTY, which is what we use as our client to connect to the board, we go ahead and load it up, and this is what we are greeted with. If you go ahead and type help in all caps, it shows all your options that you can do to set the SSID, the password, the IP address, the sensing period, and the buffer size, as Vlad was talking about in his coding section. So just as an example, if you want to set the sensing period to something other than the default, you can go ahead and set it to like 40 milliseconds. I'm going to go ahead and set it back to its default of 33. And then all we need to do is just go ahead and start, and it should be, so it starts perfectly. The data packets are sending successfully, and we can go ahead and then also start the UDP server. And as you can see here, the UDP server is also, so what we just did is we disconnected the board from the computer, so you can see it's right here in my hands away from the computer, and the UDP server is still getting all of the measurements from each of the 4 ultrasonic sensors right here. And these measurements are what we used in our analysis portion of the project, and I will go over that next. So as we can see here in these graphs that we coded a little script in Python to visualize the data that we are receiving, and we used the mean and the standard deviation from each of the sensors. So we have sensors 1, 2, 3, 4 from the left hand corner to the right bottom corner, respectively. And what these graphs show here are that the overlap of the sensors means that we get a full range of 138 degrees that we measured using the shoelace that we were talking about earlier. And after that, we can also see that there is no dead zones in the functioning of these 4 sensors. Moreover, when we look at the minimum and maximum distances, we see that as the maximum distance increases, there is a threshold at which the standard deviation increases so much that the data isn't very reliable. And the same can be seen as the maximum distance decreases and we go towards an object. So both of those were very successful. We also tested the ultrasonic sensors with 3 different objects, namely a book, a paper towel roll, and a Ziploc bag, and all 3 of them were pretty accurate, and they all had about very similar data readings. So that pretty much about covers our project for the final ultrasonic sensor, and if you have any more questions, please feel free to email us. Thanks.